Okay, I'd like to talk about, or try to answer, the question that's posed in the title. When did the Earth's magnetic field start and how has it contributed to the preservation of life? And as a bonus, if I have some time, I'll talk about a question that brings this question about the very early Earth to today and to the future, and that is whether or not we're in early phases of a geomagnetic reversal and how that'll actually affect life. I will easily walk outside of this little square here, so you'll have to constantly remind me. This picture is meant to compare Earth and Mars. Of course, they're not close together, but I want to point out a few things about this. At least in our view, at 4.2 billion years ago, Mars had a magnetic field and Earth had a magnetic field. And they both had oceans. So that's in the Hadean time period. But if we look today, we had very different planetary evolution. Okay, we have Earth, of course, with its ocean, and it has a magnetic field. Mars has no ocean, it's dried up, and it has no magnetic field. So it's really, we want to use this as an example to kind of look at how, and try to understand how these planets evolve differently through time. You've heard about comets today in several different contexts. Let me just start with this question of why comets have tails. Okay, the easy answer, of course, is that as this kind of dirty snowball, as was referred to today, approaches the sun, they start to melt. But that doesn't tell you why it has a tail. Okay, it has a tail because this is sort of a manifestation of the invisible. The ice ball is moving through space, but space is not empty. In fact, it is being sculpted by the solar wind. So we have this constant stream of charged particles emanating from the sun. Okay, and that's actually shaping the melting, and that's why we have a cometary tail. But this is actually very, very important now, because we have this constant stream of particles. Without those particles, we'd have a situation where we can have this kind of solar wind interacting directly with Earth. And that's not happening today because we have the magnetic field of Earth, which is generated in the core, produces this magnetic shield, or in the form, what we technically call this is the magnetosphere. Now, the details of this are kind of shown here, but in simple form, the importance here is that we have a pressure balance. Okay, it's a pressure balance between the force that's being produced by the solar wind, these charged particles, and mainly protons, that are constantly streaming out of the sun, and the magnetic field, which holds them off. Okay, so this pressure balance is shown here, where we have the Earth's magnetic field strength versus the solar wind pressure. And that actually defines something we call a standoff distance, which is that distance here. Now that can actually change. It can change if the solar wind pressure increases. It can change if the magnetic field changes in intensity. So it's kind of a very simple concept, but it describes to first order what's actually happening. Okay, let's see if we can start this. Now, as an illustration, we have a spacecraft that's in orbit right now, NASA, the MAVEN mission that's going around Mars to study its interaction of the solar wind. Now, Mars, of course, is a planet that's dried out, but it still has a thin atmosphere. It has no external magnetic field, and it's being pelted by the solar wind. And we can have the solar wind now directly interacting with the thin atmosphere. And there will be a tendency for these, the solar wind now, these charged particles, to pick up an ionized material and to further thin out the Martian atmosphere. Okay, that's actually something that can be observed today. Okay, we can go on. So to first order, the principal difference between Mars and Earth is one where we have this direct interaction of the solar wind with the planet, whereas in Earth, we have the magnetic field of Earth, which is standing off the solar wind and helping to preserve Earth's atmosphere. So when we think about when Earth's magnetic field started and how it has contributed to the preservation of life, what we're really asking is, when was Earth's magnetic shield in place? And it's also important to kind of think about, I've talked about this kind of constant stream of materials coming out from the sun. Sometimes the sun gets pretty angry and actually has something that we call coronal mass ejections. Now, if we have another movie that actually shows one of these captured by NASA. So you can see they're starting to develop. And a coronal mass ejection is when we actually have part of, a substantial part of the atmosphere of the sun kind of ejecting outward. Now, these will eject in all different directions. And occasionally, one of those will actually be hurled toward Earth. And you will famously know about these when you hear about, for example, auroras at low latitudes. Even at that case, Earth's magnetic shield is effective, but not effective enough to prevent some charging of the ionosphere or surrounding Earth that produces these kind of northern lights or southern lights at low latitudes. Oops. Yeah. So it turns out that the sun was actually much angrier when it was young. And why is that? How do we know this? So again, as some of the previous speakers were alluding to, we now kind of bridge more into astronomy. And we use solar analogs. These, again, are stars that are similar to the sun, but of different age. So now we think that stars all kind of follow a kind of constant evolutionary path if they start with a certain size. So we can use these astronomical observations to obtain estimates of the past solar winds from these stars. Okay, so that's how we know that the solar wind pressure was actually much larger in the past, certainly in the Hadean. Now, there's a little bit more detail here. You'll have the slides, but let me just walk you through a little bit of this. We know this from observations. We also know this from theory. And the theory is that, let's start with a very young star. Stars actually decrease rotation with time. They start spinning very, very rapidly, and the evolutionary path is to actually start to slow down. As they slow down, this process of slowing down, they're actually shedding mass. Now, what kind of rates are we talking about? Well, -13 mass units. So a very, very tiny amount of mass relative to the size of the star. But in terms of solar winds, it's actually really important. That means very early on, the solar winds would be orders of magnitude greater than they are today. Now, the young sun, young stars are less bright, less luminous. But because of this rapid rotation, they actually have other parts of the radiation, this X-ray to far ultraviolet, that's also orders of magnitude stronger. Why are these things important? Well, this, when it actually impinges upon a planetary atmosphere, will heat it and make it expand. Then we have these higher solar winds. That actually means that they're easier to erode away if we did not have a magnetic shield. So the conditions for the preservation of atmospheres are not very favorable for the very beginning planets. So that's why magnetic fields are really important. in terms of preserving atmospheres and setting the conditions for the development of life. So when was the magnetic shield in place? Well, as was alluded to earlier in some of the talks, we don't have a history of the very earliest events because of this lunar forming event. Okay, there's going to be this period where we have sort of a magma ocean, and we have no rocks preserved from that time interval. But we do later in the Hadean, we'll get to that. But the ultimate start of the Earth's magnetic field, the geodynamo, may actually be related to the lunar forming event, which again is not intuitively obvious. Why would the magnetic field start? Because you have this large impact. Well, to understand that, let's think about how the magnetic field is generated. Now, the Earth's magnetic field generation is still debated by some, but certain parameters are agreed by everyone. We have to have rotation, but we have to have buoyancy forces. We have to have what we believe convection in the liquid core. And this is really important because we need to twist the field lines. The really magical thing about Earth's magnetic field is that it is self-sustaining. Okay? It's not decaying away. We can make experiments and we can make a magnetic field. But if we impose a magnetic field, the tendency is for that to just kind of decay away with time. Earth's magnetic field does not. But actually, there has to be some process that sustains the magnetic field. And we believe it's the twisting of field lines within the core that's really important for doing that. Now, how do you twist the magnetic field lines within the core? Rotation is one component, but you need to have convection also to put further twists in the magnetic field lines. So if we just think about, this is just one example of a numerical model, an equatorial slice through the Earth. Go ahead. Where we can see that this is the solid inner core, this is the liquid outer core, and in this particular model we have the hot is red and the blue is colder, still all liquid, but we have this kind of twisting around a material, convection within the core. That's what's happening. This is just a model of what may be happening today. So, what would happen? Let's imagine our Earth before the lunar forming impact. Okay, we have material that's accreting together, forming a protoplanet. There's actually going to be a tendency for it will form a core. The more dense material will sink down and form this core material. But as things kind of gradually accumulate, there's going to be a tendency for the material to separate out according to density. And of course, there are various experiments here. This is one from Martha Stewart, no less, where you can make a density column, and you can show that fact. We have these layers, and this is just using common kitchen materials. And you can drop materials in here having different densities and see them find in their appropriate layers. But in this particular case, the point here is that we have this stably stratified layers. Okay? This is really bad if you want to have a magnetic field, because this prevents convection. So the idea is that the lunar forming event would have destroyed this layering. It would have thoroughly mixed material, both in terms of the compositional layers and in terms of the material itself, because things would have been taken to high temperature. So that's why the lunar forming event may have actually been really important for starting the geodynamo. Okay, if we can just, yeah. Now, what data do we actually have on this? The data that we have is from the field of paleomagnetism. So paleomagnetism describes studies of the ancient magnetic field. When rocks form, okay, particularly igneous rocks as an example, we have samples, students here sampling a dike, a volcanic unit that was intruded into other igneous rocks. These rocks have magnetic minerals in them, and as these magnetic minerals cool, they can acquire magnetization. So by studying these ancient rocks, we can get a track on the ancient magnetic field. Now, we've developed a particular version of paleomagnetism. So who here has actually had a cassette tape? Ah, okay, quite a bit. So when we talk about this in classes, of course, and you talk about cassette tapes, you know, students think you're from the very distant past. But fortunately, there's been this movie, Guardians of the Galaxy, so that you can refer to that now has brought back the concept of cassette tapes. The important part about cassette tapes in this context, however, is, you know, what's actually, you know, why does a cassette tape work? If you look at the tape, it's just tape. Well, the tape actually has magnetic particles in it. Of course, so small that you can't see them. And in magnetism, small is awesome. Small is awesome because they can actually, these tiny magnetic particles can record the magnetic field on billions of years timescales. So some of the measurements that we have done is to use this kind of concept. And rather than taking, this is an example of a core of lava from Hawaii, we can look at individual crystals, in this case feldspars, from this piece of lava. And within those, this is a magnetic separate, we have these tiny magnetic particles that are now nanometers in size. And these can retain their Earth's magnetic field records for billions of years. We use a very sensitive magnetometer, something called a squid magnetometer, a superconducting quantum interference device, and even more sensitive instruments where we start to get down to the physical limits of recording magnetizations. So we really kind of push the technology to record the smallest magnetizations possible. And this is important because we want to, if we want to look at the ancient magnetic field, we want to get things that are the most pristine possible. This is a zircon. We've heard about zircons in several talks now. They can be more than 4 billion years old. And in terms of the scales, this is 0.92 millimeters. Again, really hard to get a handle on, what does that number mean? As Steve was mentioning, we'll have a scale here now versus the euro currency, but the US dime. I'm going to take a look at the little writing in here, and particularly God. So there's our zircon. So that gives you an idea of the technical challenge that we're going to measure. We're going to measure that, and it has magnetic inclusions within that we're actually providing the magnetization that we're measuring. And that's why we need all this sophisticated equipment to be able to measure something like this. Well, this is our concept of what magnetic field strength would be back in time. Various studies in the different colors. The racing field is shown here with its variation in blue, and these are the data that are available. There is more or less agreement in values here in the Paleoarchean. These data are from the zircons, and there's always going to be arguments about these because these are so old, these are so ancient measurements. But so far, we see evidence for the magnetic field that appears to be present. There are big gaps in the record, but to first order, we think that the magnetic field may have been present during the entire time. So, kind of in review, we think about magnetic field and why it's important for life. We're really thinking about magnetic field of a planet like Earth versus the sun. Because the sun, or any young star, is not going to be kind for the development of life. It is, of course, crucially important for providing some energy, but it provides too much energy. It can strip a planetary atmosphere. So we have this constant material being ejected out. That's the solar wind. Okay, that's what's shaping a comet. The solar wind was much more intense for the early Earth. We know this from astronomy and astrophysics. Magnetic fields can deflect the solar wind, and the proto-Earth's core was probably stratified, like this density column, inhibiting the convection needed for the generation of magnetic fields. And the paleomagnetic data so far suggests that we have a seemingly uninterrupted magnetic field since the Hadean. So, when did the magnetic field start? Probably shortly after the lunar forming impact. There's some formatting problems in your book, but this was the best age data right now suggests that this occurred about 60 million years after the formation of the solar system. So a very early event. And there's every reason to believe that the magnetic field could have started quite soon after that. The magnetic shield was responsible for preventing this kind of early massive atmospheric erosion when the young sun was kind of pelting the Earth with all these charged particles. And was also likely important for preventing even a slow loss of the atmosphere and water throughout its history, preventing Earth from becoming Mars. Okay. Seems I have some time. Are we in the early phases of magnetic reversal, and how will this actually affect life? The Earth's magnetic field can reverse its polarity. It turns out that one state is as favorable as the other state. So we have a kind of stable magnetic field, but during reversal, it can be actually quite complex. So this is kind of one of my favorite images from NASA. And it's an image because it's really fascinating for several reasons. It's an image that was really taken by mistake. This is an image where we had a camera on one of the NASA spacecraft. And it was in a testing mode, so its lens was shut. But when its lens was shut, it turned out to be a tremendous proton counter. So you see that this spacecraft camera showed this anomaly where we have all these proton counts as it's going around its orbit. It turns out that this corresponds to something that we call the South Atlantic anomaly. It's a region where the Earth's magnetic field is unusually weak. Now, the Earth's dipole magnetic field has been decreasing, we know this from observatories and satellites, over the last 160 years at a very rapid rate. Now, if we extrapolate this into the future, and that's an incredible extrapolation, 160 years, and you're going to extrapolate this now into the future. But let's just do it. We would eventually get to a point where the field could actually become excursional in a little over 1,000 years from now. An excursion is where the field starts to move toward a reversal, but doesn't go to a complete reversal, but comes back. Now, why would we even think about making such an incredible extrapolation? Well, we think about this because this rate of decrease is so rapid, it's similar to what we see during the best data from excursions, or actually have been produced by Carlo Lage. Now, if we went back and it continues to this, and Katerina Cassell, in 2,500 years, we might actually get to a magnetic reversal. Again, just incredible extrapolation, but why would we even think about doing such a thing? Well, this is a look at the Earth's magnetic field at the core mantle boundary from a model. Now, the important thing here is the cool colors are the northern hemisphere values, kind of the greens and the blues. And the reds are southern hemisphere values. So this is the field that if you were on the core mantle boundary, this is the field that you would actually record. So let's see if we can run this one. So you see things moving around. We get to this point. Look at this. There are patches here that are in their wrong hemisphere. So that means that if you are at the core mantle boundary, the field is actually reversed. That's an intriguing thing. And we have this very rapid decrease of the field, and we have these, what we call reverse polarity flux patches starting to form. And we think that these are responsible for the South Atlantic anomaly. So again, intriguing things, suggesting that maybe what we see in these modern changes are actually more important. Now, what is the historical context for this? It turns out we have, again, we can study the Earth's magnetic field back in time using paleomagnetism. It's a particular field that we call archaeomagnetism, the study of the Earth's magnetic field on archaeomagnetic timescales or archaeological timescales, so thousands of years. It turns out that there's hardly any data from the southern hemisphere, and particularly none from Africa. So we've recently been working in Africa. This is a region in southern Africa on the border between South Africa, Zimbabwe, and Botswana, something called the Limpopo River Valley. And the Limpopo River Valley is important because the people who migrated here during the Iron Age, they were the first people to use agriculture in the region. So rainfall was really important to them. They developed a ritual where if during times of drought, they would burn their villages down and start anew. This is an example of some modern grain bins, and these are made of clay. Now, this, of course, is a terrible thing for the cultures. Ironically, it turns out to be a great thing for science. And why is that? It's because this clay material, when you fire it to very high temperatures, and then it cools, it has magnetic minerals, and it can record the Earth's magnetic field. So these essentially can act like mini magnetic observatories. So we can go back to locations, and we've done this with our students and archaeologists from Africa, and recorded the Earth's magnetic field from South Africa back in time. And what we see is around 1250 AD, we see changes similar to what was happening today right now. So that we have a decrease in the Earth's magnetic field, and it recovered. So we seem to see recurrent behavior in this region. We have drops in the magnetic field to very low levels, and then a recovery. But why would we have this kind of recurrent behavior in this region? Well, one of our ideas on this is that we have this recurrent behavior because of, this is the South Atlantic anomaly. There's this region in the mantle that's actually very unusual. Okay, there's a huge region which is unusually hot and dense. This is something that we call the low large shear velocity province. Terrible jargon, but what this means is that when seismic waves travel through this region, they slow down. And this means that there's something unusual here, and we've put forth a hypothesis that essentially, shown here in terms of the math, but as the core is actually flowing past this region, the flow can actually be perturbed. That's nothing more complicated than a river stream and eddies forming. And if eddies form, then the magnetic field, we can actually start to develop an anomaly in the magnetic field. So what we think may be happening is that because of this unusual mantle underneath Africa, we may be forming eddies, and eventually one of these is going to lead to a magnetic reversal. We don't know if the present day one will. It might. But This is at least is our hypothesis about how magnetic reversals in this region could actually start. If you'd like to read a little bit more about this, this is a general interest article on this that's published in The Conversation. You can just do a Google search on this. So, in reviewing this part, we have a rapid decrease in the dipole magnetic field. Okay, well established. Well established that this is in the South Atlantic anomaly region. Field reversed patches at the core mantle boundary, also well established. And we see similar behavior in the past. Are we in the early phases of magnetic reversal? Well, it's a little bit too early to say, but certainly we can say that this is not usual. There's lots of kind of evidence here that are very similar to what happens in the beginning stages of excursions and reversals. Turns out that, and why I'm kind of ending with this part here, is that this does have societal impacts. If the field continues to decrease, even without reaching a state of a reversal, okay, we can have damage to satellites and infrastructure. Remember, we talked about the solar wind, we talked about coronal mass ejections. So the magnetic shield is still important for us today. Now, if a satellite happens to be going through the South Atlantic anomaly and a coronal mass ejection happens to be coming at the same time, you can have damage to the satellites, and this has happened in the past. We could also have increased damage to power grids if the magnetic field starts to decrease. Now, if we reach half the field strength, kind of this excursion, we can actually start to see atmospheric effects, ozone loss, and increases in skin cancer. But don't worry. There's no mass extinctions. Okay? There's no evidence here that life is all going to be wiped out. However, if you want to give advice to people 1,000 years from now, suntan lotion would be really important. Okay, if you want to learn more about that topic, there'll be a great topic of the great debate in series, Natural versus Anthropogenic Threats for Life on Earth, and this will be on Thursday at 1:30. And with that, thank you for your attention. I'd like to take any questions.